we're starting to get into this methods of integration, which is one of the I don't want to say it's the hardest thing in the class or anything, but it's definitely a trickier concept. And the idea is we're thinking about doing these antiderivatives, right? That I'm now boxing in blue there, where we have the little f and we make it into the big F. And we've also talked about doing it with bounds. That's how we get area under the curve, right? So that's sort of the places we've been. And we're now starting to get into, like it says here, more complicated functions. And so this is the progression. When we were doing derivatives, we moved from simple rules to like chain rule, product rule, quotient rule, right? And so now we're trying to think about undoing those rules in some sense. And so you can see we're going to look at the substitution method. That's this topic. That's going to be in this class and over the next couple classes potentially. And this is the last thing that'll be on the next test. And then integration by parts, that's the next topic. And you can see here right away under the substitution method, this is the chain rule, right? I just box it in. And just to do a quick reminder of what that would look like, it's like if we were going to differentiate x squared plus 6x plus 1 or something cubed, right? You have that function inside of something being cubed. That makes it a chain rule. And I think, I don't know, I think at this point, let me just move this over to, I can have a little more room. I'm pretty sure at this point, people feel comfortable with me just kind of writing this answer down. Right, so that's the f prime g part. And then you multiply by g prime. And so looking at the thing on the left here, this is my f prime of g of x situation, right? And this would be the g prime, right? And remember, I'm just trying to remind you of this because we're going to integrate that now, right? If you look below in the notes here, we're about to integrate this thing that I'm just trying to remind you of. And so it's helpful to remind ourselves, if we're trying to undo this, it's helpful to remind us, how do we get there in the first place, right? That's what antiderivatives are doing, as you know. They're undoing the derivatives. So we're trying to undo that. We're trying to think about, how do we get there? And so I guess the thing I'm trying to point out here too is, when I kind of zoom in and I look at this thing we just wrote down, and let me get this out of the way, I can identify the aftermath of it as a chain rule, because I'm kind of looking at this thing and I'm saying, okay, here's a part of the function that has something inside of it, right? And the thing inside there, if I took the derivative, it's something else in there, right? If I do d over dx of that thing, it's something else that's in the problem. And so without knowing this first part, so let's pretend I'm going to cross this part out, right? We don't know what we took the derivative of. If we were just looking at the derivative, we could still identify it as having been a chain rule, because I'm seeing something that when I take the derivative, it's also in the problem. That's what I'm trying to say here. And so that kind of intuition is important, because that's exactly how we're about to approach these problems, right? And that's exactly what it says right here, right? So there's a bunch of steps here, but the steps say, let U be G, and G is the thing that is inside something else. And when you take the derivative, it's also in the problem, right? So we already have this intuition from the chain rule from the derivative section, and now we're just trying to undo it in the integral, but we're using the same kind of intuition is sort of what I'm trying to say here. So let me erase some of these highlight things and add some actual words. Sometimes it's hard to convey what I'm trying to say on the iPad here, so I'll try to highlight it, but it's good to add a couple words here. So we'll go through these steps in detail as I do an example, but I think the first step is important. We're going to let U be G of X, and G of X is going to be the inside function. And the other note we should be aware of g prime, when you take the derivative of that inside thing, that needs to also be part of the integral. All right, that's how we identify these as being substitution problems. All right, I'm just trying to do that same intuition that, like, how do we identify something as a product rule, right? When we were thinking about that, how do we identify it as a chain rule? We're trying to identify these as substitution rules. And what I'm saying is you need to have a composition thing, right? Something inside something else. And that inside thing, the derivative, is also part of the function. So I'm going to, as I said, I'm going to go through these steps one by one, but I'm going to go through them as part of this first example. Okay, so I'm going to kind of keep flipping back and forth between those things. And so, look, this is kind of a tricky looking integral, right? There's a bunch of things being multiplied in there. We don't know how to do that yet. And so that's sort of the first step is, hey, does this look like any of the rules we have? And I would say, no, it definitely doesn't. So it doesn't follow any of the rules. So I would say it doesn't fit existing rules that we have. I'll say existing antiderivative rules. But notice the following. Notice that something is inside something else, right? So notice 1 plus x cubed is quote unquote inside an x to the fourth, right? When hopefully that makes sense just from the chain rule kind of stuff. And if we took the derivative of that thing, 1 plus x cubed, we would get 2x squared, right? And I also see an x squared in the integral. All right, so kind of thinking back to the thing we just said a second ago, this fits the bill, right? It's got a composition, and the thing that's on the inside, the derivative of that thing, is also part of this problem. And so this is just screaming at me, this is a substitution method. Or I should say, use substitution method. So that's kind of the first step in these problems, right? Is how do I identify which method to even use? And if you have a whole bunch of problems just sitting on a page in front of you, it's helpful to know which one to jump into, right? So this is how we identify it as substitution. In other words, a chain rule gave us this thing. So let's figure out how to undo that chain rule. Is that first sort of intuition part? See what I'm saying there? We haven't really gotten into how this works, but you see what I'm saying about composition and derivatives. I'm going to try to take this real slow. I was just looking ahead at these notes. If we could get through this page and some of the next page, that would be great today. So just a couple problems that we very slowly go through, but people are asking questions about things that don't make sense. That's what my ultimate goal is. If we go through it really slow and you don't ask questions, it would just be a waste of time. So it'd be great if along the way, you just let me know if there are things you want to hear more about. Okay. Seems okay so far? I think I can get those questions up there. The steps. Okay, great. So step 1 says we should let u be the inside thing that the derivative is also part of the function. So that's, we haven't actually done step 1. So let's do step 1. So step 1, let u equal 1 plus x cubed. Right? Because it fits the description. It's on the inside, and the derivative, which has an x squared, is also part of the function. Step 2 says take the derivative of that thing. Right? So take the derivative, and then step 3 says rewrite it as du equals g prime dx. So let's do steps 2 and 3. So we're going to do du dx. So we take the derivative of u with respect to x is 3x squared. So that's step 2. Step 3 says solve for du in terms of dx. So that just means do this. Just multiply the dx over to the other side. Just going to pause right there. I've done a couple steps. See how that looks. I'm going to slide this over too. It's okay so far? We've done half of step 3, and so I just want to pause and see if a lot of this is notation. I know the notation, if you haven't been following along, can be pretty tough, right? Remember what du dx means? It means take the derivative of u with respect to x. And then I just multiplied the dx over to the other side, right? It's like I just took this thing, you move it over, and it becomes the dx over on the other side. It's okay? The thing I want to hone in on is the second part of question 3, or step 3 that I'm now highlighting. Right? It says carry any constants that don't exist in the integral along with du. And so I'm looking at this problem, and I'm going to highlight some things, so it'd be good to look at this because I'm going to erase it afterwards. I'm looking at the problem, and I see that x squared is part of the problem, but not 3. Right? So x squared I'm going to leave on the right, but since 3 is not part of the problem, I'm going to move it over to the other side. Maybe I'll leave that highlight. That's okay. Sometimes it gets kind of busy, but that looks okay. And so in other words, when you divide by 3, 1/3 du equals x squared dx. And that is something that's going to be important. And maybe you'll see why in a second. I'm not going to explain too many details before we finish this one, and you can let me know what that looks like. So let's do step 4. Step 4 says substitute in u and du. And here's what I mean by that. So I'm going to rewrite my original problem. And the idea is, based on the work we just did, I can take 1 plus x cubed, and I can replace it with u. And then I can take x squared dx, and I can replace it with 1/3 du. Right, those things go into those two locations. And then the integral, which is really complicated right now. That's something I haven't really fully appreciated. This is a complicated integral. We don't know how to do it yet. But after we make that substitution, look what it becomes. It becomes something that's not so bad. It becomes integral of u to the 4th times 1/3 du. And the 1/3 part is just a constant, and so that can just come out front and be this. And that is a super easy integral. All right, so I'm just going to pause there and let you think through that real quick, those substitutions. But the whole goal is we started with something really complicated, but we identified it as a chain rule thing. And so we're trying to like figure out the parts of the chain rule and make a substitution, right? It's called the substitution method, to make it easier to work with. And that's the thing that's super important, right? This thing we started with is really hard. This thing that we transformed it into is really easy. And so that's the whole point there. And we haven't finished it yet, but that's, appreciate that that just happened, right? We started something hard, but we transformed it in something easy that we can do. I'm going to finish it in a second, but thoughts about it so far? I'm going to wait like a full probably minute just to let people think about that substitution part.
So I see how you substituted it, but why, looking at like the original 1 plus x third raised to the fourth times x squared.
But why what? I'm sorry.
But why, like, did we have to do this looking at 1 plus x third to the fourth times x squared? Like, what
Yeah,
was
so the
wrong with
original
that?
problem, if we kind of let me bust out the antiderivative rules. Where do they go? Do they? Oh, they're part of the notes. I forgot. That's not what I want. I want the notes. If we just kind of page up to the antiderivative rules, this doesn't fit into any of these contexts. So maybe you're kind of thinking, oh, it kind of looks like this rule. We don't just have x's by themselves because one of them is like a polynomial raised to a power, and that thing is multiplying another polynomial, right? So none of these rules fit into the problem that we have. It's more complicated than that.
We
One
got to
thing
do
we
something
could
else.
do, it's a mess, right? So one thing, like if we have the problem currently says, even this alone is too much. It doesn't fit into any of these things. You could multiply 1 plus x cubed out 4 times, right? That's what it means to be raised to the fourth power. But that would also be a nightmare. It would eventually be a polynomial that you could use the anti-power rule on, but that would be, I mean, just doing that alone might take longer than the substitution rule, plus maybe you make a mistake along the way, et cetera, et cetera. See what I'm saying about that? So this could be transformed into an anti-power rule, but in its current form, it's too complicated. Other questions like that? Clarificational things? I'm going to get back to that. Maybe erase this. Oh, we're in the notes, right? Also going to get rid of that orange stuff. I just unerased all that stuff, I think. Okay, I'm going to finish this one. Are there other thoughts before we do that? So we just integrate u to the fourth, right? U to the fourth is an anti-power rule. That just becomes u to the fifth over 5, right? And so we ignore the 1/3. We do u to the fifth over 5 plus c, right? Super easy, quote unquote, anti-power rule. Right, and then we just substitute u back in. So we kind of like remove the hard part, do the easy integration, and then we put the hard part back in. Very similar to the chain rule, right? And so that would look like this. So first of all, 5 times 3 multiply together to give you 15, right? And then you plug u in. Maybe, yeah, well, I'll do it in 2 steps just in case people are confused about that algebra. So first I'll plug u in. And so from here to here, you just plug u back in. And then what I was saying was the 5 and the 3 in those fractions multiply to give you a 15 in the bottom. So that would just be like a last simplification. Not even really needed. If this is the test, this would be a great answer. But if we want to be complete with our algebra, we could multiply the 5 and the 3. And the thing I would point out is you can always check your work. And it's a good exercise for that matter, checking your work on this. Right. And I'll say it like, oh, isn't it obvious? But it's not obvious and it would take some work to check it out. But notice, and go ahead and I would encourage you to check this. If you took the derivative of the thing we just found, you would get back to the original. Right, the c goes away because it's a constant. Bring down the 5 and subtract 1 off the power. That'll give you the first term. And then the 5 and the 15 cancel into a 3, but then when you multiply by the derivative of the inside, it cancels that too. I know I'm kind of just spitballing it there, but just pointing out, hey, you can double check your work here and be sure that you got the right answer. And that is definitely something you should be able to do. Right, take the derivative of that thing I just wrote there. It's a chain rule, of course. Okay. Really just going to pause again here and see what's what. Anything? If you're a little intimidated, it'd be good to ask a question. Don't feel intimidated. There's definitely one of those things that can feel like, whoa, but then like once you see a couple, you can work it out. But take some effort, and sometimes you got to ask some questions. Anything so far?
That orange line or the orange circle that you drew from x squared, where it says du equals 3x squared, and you
Yep.
connected it to the other side, x squared.
Yep.
Didn't we get this 3x squared from taking the derivative of the inside of the first function, like the 1
Yes.
plus x cubed?
Yep.
So are you saying that this x squared is not correlated in any way to the other x squared?
No, what I was saying was when we looked at the original part, and the reason we made this move in the first place is when you, let me get another color going. When you take the derivative of this thing, you get part of that. That's what I was trying to show here, right? You take this derivative and you get part of the stuff that's in there, x squared. But what I was trying to point out is 3 is not over in here anywhere. That's why I wrote no. Maybe I should write 3, right? There's no 3 in there. And so that's what made me move the 3 over to the other side, because there's no 3 in the problem. And what we're going to see in the next one is the opposite of that. So let me maybe clarify this. I'm going to in red write something in here. If there is a 3 right here, then you'd have a 3x squared in there, and then we wouldn't divide the 3 over. I don't know if you see what I'm saying. I think the next one will kind of illustrate this idea. But does that clarify a little bit what I was trying to point out with the orange that you're asking about?
Kinda, not really, honestly.
Okay, let me do this next one and let me know if this clarifies what it at all.
All right, thank you.
I think you'll see. I hope you'll see something about this one. So, and I would ask everyone before we get started on this one, what's the inside thing in this next piece, right? That's usually what we're trying to think about with substitution. We're trying to think about what is inside something else. Ideas about that? What's inside? Yeah, so someone was a little coming through choppy to me, but I also see it in the chat here that 12 minus 5y is definitely inside something, but it's not x squared. If it was inside x squared, it'd be in the numerator, right? So what's it inside?
That's the negative
Five
square.
squared.
Yeah, 1 over x squared. Just a small thing. Obviously, if you realize it's inside something, but just to be clear, it's inside a 1 over x squared, which is going to help us with our derivative. And the other thing that you should notice is that when we take the derivative of that, we get the number 5. And so to the point that was just asked a second ago, that's a constant, but 5 is also in this problem, right? 5 is right here. And so 5 is part of the solution as well. So 5 is also in the problem is what I'm trying to write here. And so it starts to reveal itself. The process reveals itself once we start letting u equal blah, 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 and do all those steps. But that's just the starting intuition that's jumping us into, okay, this is a substitution rule. And I don't think I actually clarified the rest of the rules, but we did these rules, right? We got it into a very simplified thing. You integrate it, and then you just plug the u back in. I'm sorry I didn't point those out as we were doing it, but that's what we did in the last problem. And we're going to do those same steps, right? So the first step is u should be the inside thing. And so let's do that on this one. Right, so let u be what's on the inside, which is 12 minus 5y. And then we take the derivative. Now we're doing y's in this one. Don't let that trip you up. Sometimes people get a little flustered by a different variable. No problem there. Shouldn't be a problem, right? When we take the derivative, du dy, we get minus 5, right? Constant goes away, and the minus 5y just becomes minus 5. Right? Step 3 says solve du for the thing on the other side. So we're now at this step right here. We're about to do this thing. Let me do a different color though. So this is the thing that was just being asked about a second ago. And the question is, do we stop at this point, or are we going to go and do the next point? This is the thing. One of the things I'm trying to convey in this example. And so get du by itself would become du equals minus 5 dy. Now in the last problem, this is where we divided the 1/5 to the other side. We did this kind of thing in the last one. And what I'm going to try to convince you in this one is this is not what we do here. And the reason is because the thing I'm about to circle, minus 5 dy, is part of the problem. Right? I've got the minus 5 dy circled in the original problem and in the thing we're going to substitute. And so that's why we can leave it and not have to divide the 5 over, because we're going to substitute out minus 5 dy directly out of that problem just with du. Let me make that note right below that. We can replace minus 5 dy with du in the original problem. Right? And we knew that was our u because that's the inside piece. All right, let me pause there. I feel like I've written a little bit, kind of try to explain some stuff. Let me slide up so you can compare it to the last one a little bit. Right, and so we're going to keep with this. I'm not going to divide the 1/5 over to the other side. That's what we're going to work with. Let me know if it's not clear why. Or maybe it'll be more clear in a second, I'm hoping. Let me see if there's anything you want to talk about right now. So let me do the substitution. Maybe that would be helpful to see. Sometimes the algebra is really holds people back on this stuff, which is too bad because everyone can do algebra. I know you can. So the original problem looked like this. And one thing I'm trying to point out is the minus 5 in the numerator, you can kind of rewrite the problem and think about it like this. Right? The 5 is just like multiplying a fraction and it goes into the numerator is one way to think about it. It's like a minus 5 over 1. And when you think about it like that, that's what lets you see, oh, okay, well, then I'm just going to take minus 5 dy and replace it with du. How am I going to represent this? How did I do it? I did it with the red thing in the last one. So this thing is going to replace this entire piece, right? And then the u part is going to replace the inside piece. And when you do that, it looks like this. So let's make sure that this looks good to you. So then it would be integral 1 over u squared du. How easy is that?
So when you say plug the du equals -5 dy over here, so would this -5 dy just turn into a du? We wouldn't have to write anything no more?
That's right. Yep.
You wrote
I mean, that's what when you write, it took me a long time to sort of realize these things like practically. When you write something down that says du equals -5 dy, you're saying those two things are equivalent. Like the word equivalent literally has the word equal in there, right? And so you're saying it doesn't matter whether I write down -5 dy or I write down du, it's the same thing. And so, yes, just like you said, you take out the -5 dy, you're replacing it du with du, and we've just shown, or at least based on the way we've constructed it, they're the same thing. Yes. Right, kind of an analogy of that would be like, well, 8 over 4 is 2. And so in a problem, you could write 2x, or you could write 8 over 4x. And it doesn't matter because it's the same thing, because 8 over 4 is 2. Right? That's sort of the same like reasoning there. Other thoughts, other sort of clarificational things? Those are great sort of clarificational thoughts that help us understand what's going on here. We're not living through the course. Yeah.
Sorry, you might have said it already, but if you're saying that du and dy are the same thing, why do you want to replace it?
So I'm not saying du and dy are the same thing. The way that we've constructed this problem, du and -5 dy are the same thing. And we replace one with the other because it helps us go from this nasty integral that we don't have a specific rule to help us with, and it transforms it into this easy integral that we can do. That's why we make these substitutions.
Okay.
Philadelphia.
I'm sorry, did you say something, Joe?
No, sorry about that.
Anyone else? Good thoughts. Keep those coming. Again, we need to finish this, right? But this is the hard part. This is certainly the hard part. And just, gosh, look at how scratchy it looked with all my highlighting and stuff. Imagine not being here and just looking at this page and trying to figure out what's going on. Hopefully people watch the video. Anyway, I forget what I was just rambling about. Oh, I was just saying this is the hard part. Yeah, sorry, go ahead.
Are we're gonna solve this, the s 1 over u squared du?
We are, but this is not
this, and then once we solve it, because it's simpler to solve now, we're gonna plug back in our original numbers.
correct. Yep.
All right, that's fine.
But the one thing that I just want to clarify, it's fine to call it S. I refer to it because it definitely looks like an S, but I'd like to start moving into the word. It's called the integrand or integral or something like that. It just helps to realize that that's not an S, and that's like a math thing telling you to do something. Anyway, let's finish it. I'm sorry?
You said it was called what? Integral?
So, integral. This particular one would be an indefinite integral.
Okay.
Yep. Yeah, so let's do that. So we've seen problems like that, right? You just think about that as u to the -2. Super easy. Add 1 to the power and divide by it. So this is the anti-power rule. So we'll have this. And then you just plug the u back in, just like you said. But maybe I'll rewrite it like this first, right? It looks like this. And then just plug the u back in. Oops, except I don't know what u is. It's 12 minus 5y. What do you think? And if you took the derivative of this, you'd get back to the original, right? That's always worth mentioning. Is this shouldn't be a total like I have no idea if this is right situation. It should be at least, oh yeah, if I take the derivative of that, I get the original, right? So I would like to just mention that. If I take the derivative of the thing we just found, it would be a chain rule, and we would get back to the original. And again, that might be a good just exercise to practice for the test. What do you think? I know stuff like this, if anyone's feeling overwhelmed, can feel overwhelming and like, wow, I'm never going to get this. I was already having a hard time, blah, blah, blah. But at least just notice like how interesting or useful potentially that could be. You have a really complicated function you want to integrate. Maybe it's something useful. Maybe it's going to tell you whether or not you have enough money to retire. I don't know, whatever. And you can use substitution to get there. I think I'm just going to look at just one more, and I'm going to ask you to kind of think through the steps. I just don't want to jam this all down your throat on one day. But this last one I feel like is quote unquote, I'm going to skip over this middle one because this middle one is one of the more complicated ones, I would say. I'm going to skip over this one, and that would be a good one to maybe lead with on Friday. But this one is quote unquote easy, I would say, because, well, let's dig into it. Maybe you can see why it's easy. So again, I'm not going to sort of turn you loose and let you think about it yourself, but it'd be great if as step by step, if I say, hey, think about this, if you actually do that, and it'd be great if someone would maybe type in the chat or unmute and let me know. So here's this problem. It's two things being multiplied, and one of them is e raised to the sine, right? So it's a very, anyone recognizing what u should be, right? What is inside something else? And when you take the derivative, it's also inside something in the function. And it looks like my internet's unstable. Is I just chopping?
Yeah. Can you repeat that again? Because you kind of cut out for a couple seconds.
Yeah, thank you. I saw that too. So what I was just saying is it'd be great if people kind of, I'm going to do the step by step, if you kind of think through each step, and then we'll check in with each other. So I was just curious if anyone could look at this and what do we want to let u be? Should be inside something else in the function. And when you take the derivative, we get something else in the integral. Ideas? So I'm hearing sine of x. How do people feel about u being sine? Does anyone have a different thought? Does that look okay? I think that's good, right? And so that's good specifically because sine is quote unquote inside e to the x. And when you differentiate sine, you get cosine. And that's also in the function. Okay, I don't mean to write so many words all the time, but it's good to have this intuition written down. Or at least I like to have it up there, so if you don't write it down, you can come access it later. Okay. So you with me on that? You should be sine. All right, let's do it then. So u is sine. Differentiate it. Du is cosine. And then solve for du. Sorry, I actually wanted to let you think about those steps, and I just kind of rushed through it. Just get so excited sometimes about this stuff. That's really the truth. But that is one of the things we want. We want to use this thing, and we want to use this thing, and then we want to make the substitution. And so let me just see if there are questions about the work first. But if not, it'd be great if you would make the substitution. right? So this is your chance to rewrite the integral, kind of dig your hands in and see if this stuff makes sense. So take our original integral and rewrite it with the substitutions, right? Just take 1 second and see if that looks all right. And so one of the things that's just kind of occurring to me that maybe is tripping people up is things aren't in the right order the way they had been before. So maybe it would help you to, you can change the order of multiplication, right? And these things are just being multiplied. And so I don't know, maybe it helps to look at it like this if this is confusing you a little bit. Because then it at least groups the things together that you're trying to substitute. How's that look? So after you've thought through that substitution, right, u goes into the sine spot. These two things get replaced with cosine dx, right? And it just looks like integral of e to the u du. How's that look? Which is, right, that's the easiest integral there is, of course. All right, that looks okay. Then we just integrate it and it stays exactly the same, right? It's the best one out there. And just plug the u back in. That's it. This is actually one we probably don't even need the substitution for, right? I mean, we could pretty easily notice that, hey, when you differentiate e to the sine, you get what we have. I don't know, maybe some people kind of notice that to begin with, but oftentimes it's too complicated to kind of just do that right off the bat. We look at this first one. It's tricky and it's not super obvious, at least when I look at it, what should be u in this case. And so let's kind of think it through together. And remember, the thing we're trying to think about is when I take the derivative of what in here, it equals something else in there. Except I can't spell something. There we go. Something else in the integral. That's what we're trying to think of, because that's what we're going to let u be, right? That's what we substitute out. So ideas, and I'm going to try to do this one wrong first, just to be clear, but I'm just curious if everyone has an idea about what they think might be u.
1 plus x squared.
1 plus x squared is a really good choice because it's inside, and everything we've looked at so far is always, the g thing's always on the inside, right? But let me just sort of tell you ahead of time that that's not correct, but let's look at why it's not correct. And so maybe the answer is 1 plus x squared, question mark? Well, let's take a derivative and see what happens when we do that. Right? When we do the derivative of 1 plus x squared, we get 2x. And there's an x in our answer, right? And so we're accounting for part of it, but we're not accounting for the 1 plus x squared at all when we do that on the bottom. And so this is a good option, and when you take the derivative, it helps a little bit, but it doesn't do everything we want. It doesn't fully account for everything else in the integral. And so what I would mention is, so it accounts for, let me do it another color so it stands out. 2x accounts for the x in there, but it doesn't account for the 1 over 1 plus x squared. And so 1 plus x squared is I would have, when I first look at this without sort of knowing better, I would have thought 1 plus x squared would be a good option too. And I see a couple people, I just missed that in the chat. People are thinking x squared. We're going to have the same kind of issue, right? We're never going to account for the 1 over 1 plus x squared with those options. Does anyone sort of see what is going to account for those things? When I take the derivative of what in there, do I get other stuff in there? It's a tricky one. Other ideas?
ln of x.
Yeah, the ln part. What happens when you take the derivative of ln? Remember that?
1 over x.
If it turns into a fraction, awesome. And so that's how we're going to end up accounting for the things we're looking to account for. So let me just write that down. So 1 plus x squared didn't work, but if I differentiate natural log of 1 plus x squared, right, it's a chain rule. Let me do the details. It would become, you do 1 over what's inside there, which is good. And then you multiply by the derivative of the inside piece, which is also good because we're going to get an x out of that. So that's going to end up being 2x over 1 plus x squared. And that's nice because this is part of the problem. Right? We're going to account for the x plus 1 over x squared. Let me kind of highlight it in here. Right there. Not the 2. We'll have to think about what to do with that 2. But I'm just kind of trying to show why we want u to be the ln part. This is certainly the hardest example we've done, right? And so I wouldn't expect, I'm not going to try to grill you on something like this on a test, but occasionally in the homework or, certainly in applications, you see tricky ones like this. So it's good to kind of think them through. Do people see what I'm saying about how we're accounting for the missing pieces when we do that? Let me see if I can try to leave that there, but snake it up above. Okay. Thoughts about that at all? Questions? Okay, so that's what we're going to let u be. Remind myself how much room we have. We got lots of room. Okay. So, oops. Trying to do this. Oh gosh. There we go. So let's let u be the natural log part. And are there questions about the derivative? I guess I'm kind of taking for granted. Maybe we feel good about the chain rule. Does that chain rule look okay? Happy to clarify that. Okay, so that u is that. And so we just figured out that when we differentiate it, we get this, right? And the 2 is not found up above. That's the kind of thing I'm trying to point out right here, right? What happens with this 2? Well, let's look at what we did previously with that kind of thing, right? In this first example, when we did the differentiation, we noticed, oh, my internet's lagging. Let me let it catch up. Okay. In that first example, when we did the differentiation, we noticed there was no 3. See how it says no 3 in highlighted orange? We were kind of looking up at this example and we were like, oh, well, there's no 3 there. And so instead of leaving the 3 as part of the substitution, we brought the 3 over to the other side and made it 1/3. And then that came with us when we did the substitution, right? We see that in the substitution actually. And so we want to do that same kind of thing here, where we're recognizing back here that, hey, there's no 2 up in the original part. And so I'm going to bring the 2 with me when I make the substitution. I have some issues with my pen right now. Here we go. I guess I can do it in 2 steps. So this is like du equals 2x 1 plus x squared dx, right? Moving the dx over to the other side. And then divide the 2 to bring it with us. So 1/2 du equals x over 1 plus x squared dx. So these are the two things we're going to substitute. And you'll see from here on out, it turns into a really easy problem after we make the substitution, of course. And so this is usually the hard part, kind of thinking through what is u, how do I differentiate it, how do I sort of set things up? So what are their thoughts about it so far? Okay, so let's make the substitution. Let me write the original problem again. I guess I'll just copy it down as it's written, so maybe you can make that connection here. I'll just copy it down like normal, right? And what we're seeing here is that the u, and we also color code this a little bit. The u is going to be the ln, and the 1/2 du is going to end up being the rest of it. Right, so notice what I'm circling in green right now. That is exactly what's right here. Right? Let me do it like this. So that when we make the substitution, it looks like this, right? Becomes integral of u times 1/2 du, which we can think of as pulling the 1/2 out front and then just integrating the u. All right, let me pause there and see how that looks. And I'll particularly emphasize the point that we brought the 2 with us when we did that, right? We brought the 2 over to the other side so that we were able to substitute it in and bring it along. And this is now a super easy problem, right? We're just integrating u. Doesn't get really any easier than that. And so this is the hard part, or we've done the hard part, I mean. Thoughts, clarifications, anything there?
Now we just put in the ln 1 plus x squared.
So we need to integrate it first, right? So first we do the anti-power rule on the 1/2 u part, and then we plug the u back in. What we've been doing so far is setting it up so that we have something to work with, right? And so now we do this, in other words, right? This becomes 1/2 u squared over 2 plus c. Is that okay? Does that make sense? Can I interpret that low grunt as a no, it doesn't make sense?
I guess not. I guess, yeah.
Right? If we, this is the kind of thing I'm going to ask you to do on the quiz, right? If we integrate u du, it's just an anti-power rule. Add 1 to the power, divide by the power. That's exactly what this said right here. Can I clarify something about that?
Okay, yeah, that makes sense.
Why did it become u prime?
So I'm just trying to, it's a u to the 1.
Oh, okay.
I'm just trying to make it clear that I had a power of 1. Other thoughts? And so now we want to plug the u back in, right? The whole point of taking the u out is so that we can do this integration, so that we can make it easier. We do the easy thing, and then we plug it back in. Right, so this is going to be, I guess I can do it in 2 steps just in case it's confusing, right? The 2's multiply together to give you a 4, and then you can plug the ln back in. What do you think? If this one makes sense, you should feel pretty good about it. And if it doesn't, it's okay, but maybe we can talk about what part.
Is ln x 1 plus x squared u because x is in ln x?
No, we make u ln 1 plus x squared because when we take the derivative of it, we get other stuff that's in the problem. So, right, that's what I was trying to show in a couple places, but the blue thing at the top here, right? I'm trying to show like, hey, when we took the derivative of this thing, look, that's also in the problem. Right, you see what I'm circling right now that I'm going over in red?
Yeah.
X over 1 plus x squared is also in the problem after we take the derivative. That's why we want to make u ln. And what I was trying to show at the top was, in this part, why it's not 1 plus x squared. Because when you take the derivative of 1 plus x squared, you only get 2x. And so it doesn't account for the bottom part of that fraction at all.
Okay.
That's a good question. Other thoughts like that? Those are the kind of clarificational things we want to try to work out here.
Kind of like an essential question, like when we look at these problems, what doesn't work that like makes us have to do this the substitution process?
So yeah, that's a good question. It's always good to remember back at the like, why are we doing this in the first place? Because if we look at the antiderivative rules, which I keep forgetting are part of the notes, I always close it. In another class I teach, I keep them separate. When we look at these antiderivative rules, none of these, the problem we looked at, for example, just now, doesn't fit into any of these rules.
Okay. All right. Cool. Thank you.
And maybe just to expand on that further, like these are the super basic rules. And if we have something more complicated, we try to break it down and make it look like a more basic rule is sort of one way to think about it.
Mm-hmm. All righty.
Other thoughts? Keep them coming. Put this one back up here. All right, as a quick review, which is also might also help us with the quiz this afternoon, the difference between definite and indefinite integrals. Right, I'm going to put both of these on there, and that's what the homework is about. So hopefully it's clear to you. But this kind of thing is what I want to remind you of, right? When there's no bounds on an integral, like this first one, right? You have the integral sign, no numbers. That means you're finding the family of antiderivatives. So it just means you do the antiderivative and you put a plus c. And sometimes you need substitution. Sometimes you use the basic rules, but you get a function, right? And that's what we've just been doing over the last couple of days with substitution. What I want to just finish with here is how do we do substitution with a definite integral, right? So a definite integral is when there's bounds all of a sudden, right? There's a b and an a on there now. And that means we're doing the area between the function and the curve. It involves the antiderivative, but then we plug numbers in, right? So it's just like taking the indefinite integral a step further is one way to think about it. But how do we do that with substitution when you're like pulling things out and plugging things back in? How does that work, right? That's sort of what I want to think about at the end here. We'll see how far we go. Probably end up starting next class with these last couple examples. Okay, and so here's just kind of reminding you a little bit about the two differences, right? Indefinite versus definite integral. You see those two words here, right? Here's indefinite, here's definite. And we can see if we want to do a definite integral, there are two options, right? 1, 2. So I'll kind of talk about them one by one, and then we'll do an example using both of them. Yeah, okay, cool. So one thing we can do is replace the bounds. That's the first option that it talks about right here. Should I make those couple notes? Maybe it's good to just put these notes. I'm just looking at my notes and reminding myself what I wrote. So just as a quick reminder, this is the family of antiderivatives. It's particularly relevant for the quiz this afternoon. And when you do A to B, when you throw an A and B on there, it finds area. Specifically between the function and the x-axis. Please remember that phrasing. It will be important later. Okay, so I'll just kind of rewriting down what I just said in words, right? All right, let's get the actual method. So you have two options. You can either replace the bounds, or we can do a substitution and work on it that way. I think that maybe the easiest thing to do would be the substitution first. So let me work on the one on the right here for a second. So when I say substitute u back in, what I mean is you use the original bounds. So don't change the bounds, use the original one. And so the way that works is, you plug in something for u. We've been calling it g. And then, of course, we make the substitution du equals g prime dx. So I'm just going to write down the process in general so you can think through it, what it looks like without any numbers in there. And then as a reminder, what we've just been doing over the last couple of days that we just did a second ago, it lets us take this really complicated function that looks like this, right? The chain rule thing. And it lets us rewrite it as something really, really easy. And I don't mean to say really, really easy, like, oh, this is so easy, but when you look at the thing on the left compared to the thing on the right, it's obvious that the thing on the right got simpler, right? And so this method that's on the right here, substituting u back in, just says, hey, leave a and b alone. Don't change a and b. Just plug u back in and then do the integration. And so before we plug in a and b, we would do this. We would plug g back in and then go from a to b. Right? So notice what happened between these two steps. It had a u in it to begin with, and then you plugged in the g back in, right? And then when you do that, you just plug the numbers right in like we would normally, right? This is the kind of thing that I'm going to ask you to do on the quiz, for example, this afternoon. Then you just do your f of g of b minus f of g of a. You just plug your points in. And the real thing I'm trying to point out here, that the takeaway, you just use the original bounds. You don't change the bounds at all. But it's after you plug u in. Should we do this example first or look at the other one? Yeah, so maybe let's just go right onto the problem and do this example with that method. And this example we already saw. All right, this example, integral of 1 to 5, 1 plus x cubed to the 4th x squared, was the first example we did, right? And I actually referred to it earlier today. So we already know how to integrate this thing, right? We let u equal 1 plus x cubed. We do this whole thing, blah, blah, blah. And so I'm gonna go through the steps, but I'm not gonna do them in detail. If you want the detail, you can look back at this one, is what I'm trying to say here. But we can still do sort of the general process, right? So remember how this worked. You let u equal 1 plus x cubed. And that let us rewrite the integral like this. Maybe we should just do it together. It lets us take our original integral and rewrite it like this. And so that's the first step on both of these options, is just to do the substitution part. When you actually plug the numbers in is when the either or situation comes up. And so again, if you want the details on that, just look up above at the last answer, or the first example we did. But if we now want to integrate this thing, what option 2 says on the top here is just do the integration, plug u back in, and then just plug the numbers in. And I personally like this method because it's just, go ahead and do that. And then you plug u back in, and then we just move forward, right? So you integrate u to the 5 over 5. And then before we do anything, we plug u back in. And then we plug in the numbers. Right, so from here to here, we just plug u back in. And you remember this notation, again, this is the thing that the quiz is on. When you write this notation of 1 to 5 like I did, you write straight line 1, 5. That means I'm about to plug in 5, and then I'm going to subtract, plugging in 1, right? It's like a notation thing. And so we just finished carrying it out. Right? This is going to be I forgot, this should be a 15 though. Sorry about that. 5 times 3 ends up being 15. On the bottom, does everyone see that denominator just changed to 15? And so that's going to end up being 126 to the 5th over 15 minus 2 to the 5th over 15. And let's just leave it like that. You can get some decimal out, and that's fine, but I want to show you that we get the exact same expression when we do it the other way. And so I would refer to this as the basic way, kind of. This is the way that you don't have to change the bounds. You just keep doing everything we've been doing with substitution, and then you just plug the numbers in. I just want to show you a kind of a different thing in a second here, but let me let everyone catch up and see if there's some questions about that. Does everyone see where that 15 came from? It came from the 3 times 5. Thoughts about that approach? You know, one of the things I'm trying to show you too is, you know, in my opinion, calculus is kind of the gateway to higher math. I mean, there's a couple calculus classes that kind of get you up there. But eventually, once you get high enough in math, you want to be able to make sense of something that looks like what I originally wrote, which I know is there's no numbers in there, right? It's A's and B's and X's and F's and G's. But if you can kind of see how the thing on the top is the same as the thing on the bottom, or maybe more importantly, how the thing on the bottom is an application of the thing on the top, that's what really unlocks your ability to sort of learn higher math, because you can see how a general thing gets applied. Thoughts about what we just did there? Questions at all?
So you didn't what's it called? Find u prime or something? You just did it?
So I'll just remind you one more time that we did this problem previously, so I'm not going through all the details about integrating it. I'm just showing you how to plug the numbers in after we integrate it. If you want to look at the details about the u and all that stuff, you should look back at this problem.
Okay.
Right, what I did there is I said, I went right from this thing, I showed you what u was, and then I went right to the answer, because I'm not trying to do another example. I'm trying to show you how to take an example we did and then plug in numbers. Other thoughts? Okay, if there aren't thoughts, let's look at the other option. I would call this maybe the more savvy approach or something. I don't know, maybe the more, I don't know. Some people like this one better. I'll just leave it at that. So the other option is you can replace the bounds, and the idea is you don't substitute u back in. So you just work with kind of the really easy version, but when you work with the easy version, it requires you to change the bounds. And so I'm going to do the same kind of general thing here, right? So you let u equal g again, just like we did before. you again make the substitution du equals g prime dx, right? Nothing there has changed. What changes is the next part. And so our original function, which again is the chain rule, then becomes the simple f prime of u integral, of course, but the bounds are going to change, right? So I'm going to write that in red now. The new bounds are going to be, if I can get my pen working, there we go, g of b and g of a, right? So you take this g function and you plug your bounds into there to get new bounds. And the reason someone would do this is because then you don't have to plug u back in. If it happens to be complicated or cumbersome, maybe that's a nice thing. And instead, you just work with your new bounds in the easy function, right? So then instead of, notice how in the last step, we had a's and b's here. There's no a's and b's anymore. It's g of a and g of b. Right? That's the difference here. And so if we kind of kept going with this method, we would then work with our f function, and then we would plug in g of a and g of b. But notice how the thing I'm writing down right now is the same as the thing that we had last time. This thing right here ends up being the same as this expression. That's what I'm trying to point out here, and that's what we'll see in the answer. Right? In both cases, you're going to plug b and a into g. The question is, do you do it beforehand and then use the easy function? Or do you do it inside the function itself after you've plugged u back in? And so the big kind of takeaway, if you're totally confused, you have no idea what I just said, the thing that you should sort of take away from this thing I just wrote is you should change the b to g of b, and the a, you just plug it into g. And then don't plug u back in. So that's what we'll see in the example down below. Let me just let folks sort of catch up and see if there are questions about the notation. Now seeing that there was a question 5 minutes ago about 1/3. I can try to clarify that. I would encourage you, Sebastian, to look up at where we did that example and try to see where that 1/3 came from. I'll scroll up in a second as soon as folks finish writing. Thoughts about what I've written there, though? Okay, I'm going to explain the 1/3, and I don't want to, how should I say this? I don't want to be rude here, but I've explained kind of where these constants come from every period, of course. I've already done it twice today, and no one's asked a question about it. So I'm happy to clarify those things, but I explain it to try to clarify it. And if I don't hear an answer, it makes me think that it makes sense. And so it's a little bit, it's just, I feel bad that I explained it twice and there's still a question about it, right? You should ask me back when I was talking about it. So once again, when we do the u substitution, right, and then we do du dx, I'm noticing that there's not a 3 back in this original function, right? There's no 3 when I look back here. Is there an x squared? Yes. Is there a 3? No. And so I can't substitute the du for 3x squared dx because there's not a 3x squared dx. There's only an x squared dx, right? And so that's why I had to then bring the 3 over to the other side, and then it comes along with us when we make the substitution. And again, it's because the original function did not have a 3 in it sitting out front. I think it's important to contrast that with the second one we did. I did this on purpose when we did it this way. On the second one, we let u be this, and then when we did du dy, it was minus 5y, or sorry, minus 5 dy, right? And then when I look back at the original, I said, oh, good. there is a -5 and a dy in the original. I know I just kind of covered it up. Right, but you see in this original, there's a 5 and a dy. And so I didn't have to take the 1/5 over to the other side anymore. I could keep it over on the right and then make this substitution. Right, the -5 dy becomes du. What do you think? I would love to hear someone clarify that. That's still confusing. It's like totally fine. What's not fine is for me to say it 3 times now and then still be confused. You got to say something about it if it's not still clear. Anyone?
It's still kind of a little confusing.
So you do the du dy part, and then you're just looking at the original function. Oops, I think I just did something I didn't want to. Okay. Right. Do you see this thing I'm circling in thick blue now? -5 dy is on the right.
Like that would, because -5 dy is still like, you still have -5 and -5 in the bottom too. Is that why?
No, it's because it's in the top, right? So here I am rewriting the function, right? This is the same thing that's on the top, right?
Oh, because u is in the bottom.
Yeah, u is the thing that's inside the thing being squared.
Okay.
Right, so when we make the substitution, I think this is the thing that's important to look at, this thing right here, right? This thing inside becomes u. This -5 dy became du. Okay. If I can color code that, like this is here. This is now here.
And why isn't u like 1/12 minus 5y?
Because I was recognizing that when I take the derivative of just 12 minus 5y, I get something else that's in the problem still.
Okay.
Right? You get the 5 dy, and that was good because that was in the problem.
Okay.
If you let it be 1/, you're going to have a chain rule thing, and it's going to get more complicated, and it's not going to be something that's in the problem.
Okay.
Those are good thoughts. Thank you. Other things like that? Other clarificational things about the constant?
So you just kind of like take the derivative of all of them separately, and whatever is in the function, that's what you
need to think about. Yeah, so you think about, like, that's what we were kind of thinking about here, right? We tried this one, didn't work. So then that led us to this one. We tried that one, did work. And so, yeah, it takes a little bit, sometimes maybe a little bit of trial and error on certain problems. I think a lot of the ones in the homework are not super complicated. They're more like this one, right? Like, hey, when I take the derivative of sine, I get cosine. Like, there's only so many things in this problem you could possibly be. And so it's not that hard to think through ones, I think, that look like this, or like this one, right? We'll do this one next time. But hey, when I take the derivative of x squared, I get 2x. And so that one should be, right, that's sort of the level that I would hope for that you could do on a test, for example, next week.
What's it called? Can you scroll up for a second? Keep going. Yeah. Keep going, hold on. Yeah. What's it called? No, hold on. It's the ln thing. The one right underneath this one. Yeah. I don't get that one. I get that we're taking sorry. I get that we're taking the derivative of ln, so that would be 1/x, right? So that's the 1/1 plus x squared, because that's what we're doing right here. The next one is multiplication by the derivative of 1 plus x. Where are we getting that one from? So is that because that was the rest of the problem and we're taking the derivative the rest of it?
No, when you do the derivative of ln x, it becomes 1/x. Yes. Mm-hmm. But if we do the derivative of ln with something inside of it, it becomes a chain rule.
Oh.
Right, this is my f prime of g of x. This is my g prime of x.
Okay, that makes a lot more sense now. For the one all the way up top where I was talking about 1/3.
Yep.
The reason, sorry, damn, something's wrong with my throat. I don't know, it's acting up. Since we don't have a 3 in the problem like you were speaking on, we just kept it along with us because like we need this U, we need it. So like we just brought it and we made it 1/3, and then we just eventually used it. Was that it? Was that really it?
That's really it. Yeah. Right. So like it's easy to make. I think it's easier to look at this problem to see why this
Yeah, because
works.
this one has the stuff in the problem, so it fits perfectly.
Right. And so what we did is we just took this thing right out and just replaced it with du, because this literally says du is the same thing as -5 dy. That's what equals means. And so we could just take that right out and plug it right in, right? So in the other one, we didn't have that luxury is sort of the idea. We couldn't just replace the 3 because the 3 wasn't in the problem. And so instead, it had to move over to the other side, and then it's part of the du side. And so then when we make the substitution here, it comes along with the du. See that?
Yeah, so you divided it, and then that's what made it to 1/3.
Yeah, sorry, that was the problem. Yes, I divided it over to the other side, right?
Okay.
These are good thoughts. I'm glad you're thinking about this carefully. Other things?
So this is what's going to be on the test today at the end of class, or the quiz? Not the test.
No, the easy versions. No. This is substitution. Substitution, we haven't had a homework due on that yet.
Oh, okay.
It's going to be more like the homework from Wednesday.
Oh.
Okay, I would like to finish this last little part though, because we're kind of getting close to where I'd like to start the quiz. And so let me just show you, forget how we got down that sort of tangent. Oh, I noticed a thing in the chat about the 1/3. Anyway, let me just show you that if we change the bounds, I can't believe we got so far away from that. I'm like forgetting about it, so that means you probably forgot about it. The first option is we can change the bounds and then not plug u back in. That's the takeaway. So let's look at that. So let's do it down here, option number 1. And so we plug 5 and 1, because those are the bounds, right, into the u function, which in this case is the 1 plus x cubed. Right, and so 5 would change into 1 plus 5 cubed, which is 126. So that's the g of b part, right? And then the a changes into 1 plus 1 cubed, which is 2. Right, this is my g of b. This is the g of a. And so the nice thing is we don't have to plug u back in, right? We can just work with this really simple version and just use the new bounds. And so we'll have 1/3 integral of u to the 4th du, but now the bounds are going to be 126 and 2. And so some people like this method better because, right, you integrating u to the 4th is easy, and then you just plug these numbers right into that easy kind of thing. Some people get confused by it though, which is why they avoid it. You can do whichever one you like. That really doesn't matter. Right, this just becomes 1/3 u to the 5th over 5, and then we plug in the new bounds. And you'll see we get the exact same thing we just happened to get a second ago. Right, so we'll get 126 to the 5th over 15 minus 2 to the 5th over 15. So the thing I'm trying to point out here is you get the same thing. I really don't care which one you do. Totally up to you. I'm not going to force you to do it one way or the other. And so in these two problems on the last page of the substitution notes, we've got bounds on the integrals, right? So these are what we call definite integrals. And so we're going to get, some number out of this when we do the integration. And we talked about 2 different methods of doing it. You can see they're right above here. You either change the bounds and don't plug u back in, or you plug u back in and use the original bounds. And we did it both ways in both the examples up top here. I think to kind of finish off, maybe I'll just do one way and the other way, just to give you options again. And again, I apologize. I haven't actually looked at this test or this problem on the test yet, so I don't know if this is clear to you or not. But good review anyway for the final, which we'll have to do this next week. So on this problem, we want to look for something, right? We want to let u be something, and whatever u is, it should be something else in the problem. I'm sorry, when you take the derivative, it's something else in the problem. So what is u in this case? We had one like this on the test, actually, kind of similar.
X squared.
Yeah, nice, x squared. I think Janetta's realizing that because when you take the derivative of x squared, so that's going to be our u, we get 2x dx. And that's really nice because we have a 2x and a dx like right in the problem. And so we don't need to do anything funky with the constant or anything like that. We just literally replace the x squared with u, and then the 2x dx is going to become du. Right, so that makes the substitution really nice and easy on this particular problem. Gosh, my pen is having some serious issues this morning. And so the original integral, I'm just going to rewrite it like this. The original integral, we see that this piece is just the u right here, and this piece is going to be the du. And it just becomes a very, very easy, or as easy as they can get, kind of integral, right? You just go from pi over 2 to pi of cosine u. Right, so we started with this like product of a trig function with the polynomial, do a little substitution, and it turns out we can just think of it as just the integral of cosine, which is one of those easy integrals, right? We don't have to worry too much about this. We just know that that turns into, I have to remember, derivative of sine is cosine, so cosine becomes sine, right? Positive sine. And so this just turns right into, oops, I'm going to do the integration, sine of u, and then we just plug the points in. Well, before we plug the points in, we need to decide what we're going to do on that. But this is the kind of thing that, on the test, if you kind of went this far, you get lots of the points. Questions about the substitution part? Anyone still a little bit shaky on that, or? And so then remember what I just mentioned a second ago is you have two options. You can either replace the bounds and don't plug u back in, or plug in u and use the original bounds. Seen a couple examples of both those things, just in the interest of space and time here. We'll just do one on this one and one on the next one. So let me copy these instructions so I can paste them onto the next one. And then on this particular one, I don't know, let's just do, what's the second one look like? Do I want to plug pi into the bounds? Let's just not plug them in. So I'm going to use I'm not going to do this one. Let's plug in and use the original bounds on this one. Just looks like it might be easier. Okay, so instead of just using sine from pi over 2 to pi, that's where we ended, we plug u back in. Let me just pause for one moment there. Looks like I was just catching up with my internet. So I don't know what you guys did or didn't hear, but what I'm saying is, notice here I plugged u back in. So from here to here, u is x squared. And then I'm keeping the bounds, right? So it's still pi over 2 to pi. We don't have to mess around with that. We just plug the bounds in. And at this point, it just becomes a simple problem. It becomes sine of pi squared minus sine of pi over 2 squared. And pi squared is not a typical number on the unit circle. So if you're thinking like, oh, how do I do this with my head? We would use a calculator for this particular problem. I used a calculator ahead of time and I got approximately 1.05. Like pi squared is not one of those typical spots on the unit circle. Okay, what do you think about that? Feeling kind of good about substitution? I know some of you guys are kind of what I would call turning the corner where it's not that bad anymore. Kind of understand what's going on. Jeanette is just unmuting to answer questions like crazy. She's just all over it. So this will be on the final, though, just to be clear, right? This is the last kind of thing that will be on the final. Questions about that? Okay, so this next one's kind of, I don't want to call it easy, but maybe once you see what U is, it kind of is easy. It's easy. It's so easy, it's tricky almost. That's how I kind of think about this one. Right, so, and the tricky part is thinking about what U is, because we want U to be something where we take the derivative and it's something else in the problem. But that's not exactly the case here. So thoughts about what we might want U to be? Maybe just everyone think about that for 1 second. If anyone wants to type it in the chat, or welcome to unmute and say it as well. Curious what you're thinking. What would U be in kind of a not too bad of a function? Ideas?
Would it not be 12 minus 5y?
It would be 12 minus 5y. And I think why were you thinking that, Janetta? Can you clarify why that came into your mind?
Well, when you make it du, you can, get out 12, and then it would be 5y, and then just divide it by 5, negative 5.
Right. So I think what Jeanette's pointing out is when you take the derivative of 12 minus 5y, you just get a constant. And we know how to handle constants when we have this situation, right? When we have something that looks like du equals 5y, minus 5 dy, we look at the problem and we're thinking, is there a u in here? I mean, a minus 5, we're looking back, no minus 5. But we know how to deal with that, right? We just bring the minus 5 over to the other side, we divide it, and then it comes with us in the substitution. And so as long as, what Janetta is pointing out, and the reason that she sort of reached that point, so we do this, right, is we know how to handle constants when we do the substitution. And so we really just think about this as like a 1 over u squared, and we know how to integrate 1 over u squared. So let me just pause there and see if I can clarify something about that. You'll see the substitution in just a moment here. But something I can clarify so far? So let me do what I usually do, which is to rewrite the problem, right? So I'm going to just copy it over and then kind of think about what the pieces are. And so using the thing boxed in on the right there, we just said dy is going to become minus 1/5 du. And then the 1 over 12, the 12 minus 5y inside the squared is u. Right? And so we're able to make a nice substitution with this, where it becomes du. And just to be clear, that's really, you can just pull the 1/5 out front, and then it's just u to the minus 2. And that's a quote unquote easy kind of one, right? Just the anti-power rule. So let me just pause there, see if the substitution looks okay. Question? All right. So we're going to do the second method, but let's, I guess, integrate this first. So the minus 1/5 comes along. We add 1 to the power, divide by the power. Right? And now let's change the bounds. I'll still write 0, 2 right now, but on the next line, we're going to switch the bounds over. And can I paste in my thing here? Let's see if my genius plan worked. There it is. So we're not going to plug things in and use original bounds. We're going to replace the bounds this time. And so we just take u, and we take the bounds and we plug them into u, right? Let me just kind of review that by looking up over here. So the way you replace the original bounds, like it says up on this particular thing, is we change the bounds by plugging them into whatever u was, right? So like on this particular example, u was 1 plus x cubed, and so we took the old bounds, 5 and 1, we plugged them into 1 plus x cubed, and we obtained new bounds. And that just is nicer sometimes because then you don't have to plug u back in. It's just the same, it's just like an alternate approach. And I usually just like to show both of them because you can choose whichever one you like. And like we just saw in the last one, maybe it's easier sometimes not to plug in pi and pi over 2 into something being squared, for example. Maybe we just want to not do that. So let's replace the bounds. So replace the bounds. We take the 2 and we plug it into u, which was what, 12 minus 5y. And we'll get 12 minus 10, which is 2. So that one actually stayed the same, oddly enough. And then 0 becomes 12 minus 0, which is 12. So instead of going from 0 to 2, we go from 12 to 2. And we keep it in that order too, right? So in other words, it becomes u to the minus 1 over 5. I'm just kind of carrying this down over here, right? U to the minus 1, I'm multiplying those things. The negatives cancel. And then instead of 0 to 2, we're going from 12 to 2, right? Because 2 stayed the same, but 0 turned into 12. And that's something that's easy to do. First, you plug in the 2, then you plug in the 12. And I actually, it looks like I didn't do this in the calculator ahead of time, but just to be clear, the negative ones make them into fractions, right? So this is really like 1 over 10 minus 12 times 5 is what, 60 over 10? I mean, 1 over 60. That's not actually that hard to do. It would be 5 over 60. Is that right? Multiply that by 6, subtract 1. I think that's right.